The Aurora Borealis, or Northern Lights, a spectacular light show sometimes visible in the skies near the North Pole. Ancient peoples used to fear the aurora, believing it was an omen of disaster. We now know the northern lights occur when streams of charged particles, or ions, from the sun interact with the gases high in Earth's atmosphere. The atmosphere is a protective blanket of air that surrounds our planet, and we couldn't exist without it. Earth's atmosphere contains primarily nitrogen and oxygen. Nitrogen is important to living organisms. Proteins and other complex chemicals contain nitrogen. And most living organisms take oxygen directly from the atmosphere and use it to help release energy from food. The atmosphere protects life on Earth in many ways. It helps trap heat energy absorbed from the sun, which helps to maintain a temperature range that is suitable for life. It also shields Earth from dangerous levels of ultraviolet radiation and reduces most meteoroids to dust and gas before they can reach the surface. The atmosphere consists of 4 layers. The outermost layer, or thermosphere, where the Aurora Borealis occurs. The mesosphere, where meteoroids burn up. The stratosphere, where ultraviolet radiation is absorbed. And the troposphere, where all weather occurs. For hundreds of years, scientists have studied the physical characteristics of the atmosphere and have applied what they learned to better human life. Mountain climbers, hot air balloonists, airplane pilots. These individuals all rely on a thorough understanding of the properties of the atmosphere. How is the atmosphere important to the survival of life on Earth? As you watch the following segment, think about how hot air balloons have been used to advance scientific understanding of our atmosphere. Albuquerque, New Mexico. Every October, hundreds of hot air balloonists gather here for the International Balloon Fiesta.
Beautiful place to fly, all these beautiful balloons and beautiful people.
It's the world's largest hot air balloon gathering. For many of these pilots, hot air ballooning is an exciting sport. But to launch and pilot a balloon, they need a thorough understanding of one of the basic properties of the atmosphere. Warm air rises in cooler air. An 18th century Frenchman named Joseph Montgolfier is said to have discovered that principle while sitting in front of his fireplace. He noticed some ashes moving up the chimney and realized it was the hot air carrying them upward. He began thinking about the practical applications of his discovery. In 1783, Joseph and his brother Etienne launched the first hot air balloon, and others soon followed. At the time, no one knew how far into the atmosphere humans could go and survive, or that the balloon would become a valuable research tool for studying the atmosphere. One of the properties of air is that as altitude increases, air density and air pressure decrease. At 3 kilometers, about the height of the Rocky Mountains in Colorado, the air is so thin that many people have trouble breathing. At 9 kilometers, the altitude at which commercial jets fly, there is not enough oxygen to sustain life. That's why airplanes carry their own supply of oxygen. But in 1960, the United States government wanted to send a manned balloon much higher into the atmosphere, way beyond the height at which commercial planes fly. It was a risky, top-secret mission for the fledgling U.S. space program. Scientists at NASA chose an Air Force test pilot named Joe Kittinger to take on the challenge. Kittinger was to pilot a hybrid balloon, which uses a combination of conventional hot air technology and helium gas to an altitude of 31 kilometers. His mission? To test a new parachute designed for astronauts in the event that they were forced to bail out at high altitude. NASA didn't know if the parachute would work or if Joe would survive.
We had never been into space before. We knew that people had to be properly prepared and dressed and pre-breathed and trained, and it had never been done before.
One of the properties of the atmosphere, air pressure, was a big concern. Where Joe was headed, the air pressure is nearly zero. But human beings need air pressure for our bodies to function properly. Breathing becomes difficult, and it's harder for blood to circulate properly to provide the body's cells with the oxygen they need. So Joe was equipped with a pressurized spacesuit, similar to the suits astronauts use today. Joe's launch and initial ascent went well. But as the balloon rose to 12,192 meters, there was trouble.
I suddenly realized that my pressure suit glove on my right hand was not working. I had a great deal of concern about this because what happens is the blood pools if you don't have pressurization.
Joe's right hand was useless. He had to operate all the controls with his left hand. At the designated altitude, 31,000 meters above Earth, Joe jumped.
There was really no sensation of falling. There was no wind blast, there was no fluttering of my flight suit. I felt like I was suspended in space. I was weightless. I had no feeling of movement.
At 27,000 meters, Joe reached a speed of 1,110 kilometers per hour, which was supersonic at that altitude. Joe broke the sound barrier with his body. At 6,000 meters, he opened his parachute and drifted to Earth.
We had demonstrated that we could put man in a space environment, that he could do work in a space environment, and that we could also provide a means of escape from very high altitude.
These days, the use of balloons to study our atmosphere is routine. The National Weather Bureau frequently launches unmanned balloons carrying sophisticated data-gathering equipment. The information collected helps meteorologists better understand weather patterns so they can make accurate predictions. That's especially valuable for people living in the path of violent systems, such as hurricanes or tornadoes. NASA, too, continues to use balloons in its space research program. One goal is to someday send a balloon high into the thermosphere, to the very edge of outer space. As altitude increases, what happens to air pressure?